So today we're going to learn more about applications of Prolog, and that's also the theme of the homework, of course. So the reason I did that is that I was Googling around for something with Prolog, and I came across some discussion somewhere on Reddit or somewhere where one person bemoaned the fact that he was tortured with Prolog in his programming languages class, and all he could remember is that you can do append in Prolog. That was the only thing it was good for, he thought. And so I thought that was sad, and we want to know that you can do other things than append with Prolog, right? So the first thing here is this nifty puzzle here. I found this puzzle because I had another puzzle in a previous homework assignment, and then I Googled for it. The very first thing was a solution to that homework assignment, so I guess I can't use that again. And the next thing was this puzzle, because it also has to do with flipping stuff. And it's pretty nifty. So what you'd have to do is you click on one of these tiles, and then it flips, and the four neighbors flip. And your mission, should you choose to accept it, is to make all of the tiles red. And so you might say, I'm going to flip here and here, kind of. That was maybe not so clever. Let me undo that. So maybe here, right? And here, but now we seem to be kind of getting stuck.
Professor, can you do it again with the mouse so we can see it better?
Sure. Okay.
Reset everything.
Yes. In fact, I'm going to reset it and give you a solution.
Did you just memorize it?
No, absolutely. Yes.
Yeah, that works. Yeah.
Voila. Okay. So how do you do it? So it turns out that, and it's easy to see that the order in which you make the clicks is completely immaterial, because what it does is it flips those tiles, and in which order you flip them, it doesn't matter. What matters in the end is that each tile is flipped an odd number of times. If the order doesn't matter, we might as well choose an order that's easy for us to reason about. So let's do row by row. First row, then the second row, then the third row, and then left to right. Why not? So now one has to look at all the various possibilities for the first row. And so let me say I'm clicking this one here and this one, because this seems like a good idea. Now, from this point on, everything is automatic. Why? So I'm done with the first row. That was how I set it up. Then in the second row, I have to flip exactly where there's a blue one in the first row, because if I don't flip it, it'll never get flipped again. Remember, we go left to right, top to bottom. And I shouldn't flip anywhere else, because I wouldn't be able to undo it later. So I flip exactly where the blue ones are. So I flip exactly where the blue ones are. Now I need to flip everywhere. And it didn't work. Right? I can no longer fix these two, because I'm done with all of the flipping since I've committed to doing it left to right and top to bottom. So that means that starting out with position 1 and 5, it does not give me a solution at all. So it turns out, in fact, that for a 5 by 5 puzzle, there's only two possible starting positions, namely clicking 1 and 2, or symmetrically clicking 4 and 5. And so that's what your program is going to figure out. Now, how is it going to figure it out? There's two distinct tasks that need to be done. One is, if you have the flips in a given row, you want to find out how's the next row going to look like when you make the necessary flips. We know what the necessary flips are. They're at all the blue places. But you need to figure out then, what does that row look like, so that you then know what are its blue places. And then one repeats that n-2 times, or n-1 times maybe, and then one gets the last row, and if the last row is completely flipped, then you have a solution. And now you need to plug in all the possible ways of getting the first row flipped, and that's all you need to do. So it's a few lines of prologue. The hardest thing is the flipping, but it's not super hard because of the representation that I've chosen. So what I've told you is that make it so that you collect the flips in the first row in a list of column numbers, then another list for the next row, and so on. And that turns out to be a good representation to use. I'll talk about that a little bit more. So that's that puzzle, and it is surprisingly nifty that you can get all of the solutions. It's also interesting how many there are. So when you try different sizes of the rectangles, you're going to get different ones. So sometimes there's 1, sometimes there's 2, sometimes there's 4. You might want to find one where there's 8 or 16. And an extra credit if you can explain to me why it's always a power of 2. That means you would have paid attention in your linear algebra class. All right, the next one is a more intricate puzzle. So it's this Rubik's-like cube, this thing over here. So I did actually manage to solve it yesterday with all of the various twists and turns. And so it's not like a regular Rubik's cube. You have to twist it like in this diagonal way. Each of these vertices, you can rotate it 120 degrees back or forth. And then it's mean in that it has these little color markings, and they all have to match. And so it seems more complicated than a Rubik's cube. And so how can one solve one of these things? So I really did resolve not to watch videos, of which there are many. So like here is a crazy dude who shows how to do it. And so I just did not find this all that illuminating. So yeah, he goes on for 3 minutes, and so there's a whole bunch of them. No, I think she has a different algorithm.
And then if you have the right one on top but none of the centers.
And again, it was not clear to me why it was always going to work. So I figured, we should be able to do our own algorithms. And so the key to doing that is to try to come up with turns that don't do too much damage. I mean, it's a very confusing thing because everything seems to turn together. So if you have an extra $12 to spare, just go and order one. It is a bit of an experience. So we want to find out sequences of rotations that preserve as much stuff as possible. So I didn't know whether these rotations exist, but then after writing this program, I did discover that you can do the following. You can make it so that all edge corners stay where they are, and the faces get moved in some way. And it turns out it's not that hard to just by hand, you can eyeball and put 4 corners in the right place, which interestingly enough automatically puts the other 4 corners in the right place. They're going to be twisted, but that's okay, one fixes that at the end. So you're going to have the corners in the right position, maybe twisted, and the faces are not going to be in the right position. But you can discover enough moves that fix the corner positions, that leave them exactly where they are, and permute the faces in some way. There are enough of them that any of the possible permutations can be so generated. So I have a prologue query that if the faces are messed up, I put in the permutation that I need to get the faces repaired, and it spits out a sequence of usually 5 or 6 or 7 rotations that I need to execute. I execute them, and the faces are then in the right position. At that point, I have both the faces and the corners in the right position, and then there is the little matter of twisting the corners so that they're correctly oriented. The little colors are usually in the wrong way. That turns out to be exactly the same mechanism as the flip game, the first part that you're doing. And I can compute a set of vectors that show how the basic rotations are, and then I solve a linear equation. and I have a little program for that as well. That way I get all of the corners correctly oriented, and then it can happen that 2 or 4 of these faces are in the wrong orientation, that they're flipped by 180 degrees, and then there is a similar way of repairing those. And so I can do it with these moves that do as little damage as possible, and eventually I could probably get fast at it and have a YouTube video. Anyway, but so the fun part is to use Prolog to help out with these computations. And then what Prolog has been really good about is that you can do all sorts of different queries. I can say, compute all the possible rotation sequences of length 4 and 5 and 6 and 7 and 8 so that the corners are unchanged, or so that I get the following flip that I need to get the faces in the right order. And they're fairly straightforward queries. The hardest part is to figure out what is the cumulative effect of a bunch of rotations. So each of the rotations that you can do, all you can do is you can take one of these 8 corners and you can then make it twist in one direction or the other. And it turns out that it twists, you only have to worry about twists in one direction, because if you do that twice, it's the same way as doing it the opposite direction. So we're only going to look at positive twists, and if it then says you have to do R0 followed by R0, that's the way it is. And so how does one figure out the cumulative effect of doing, say, R0 and then R4 and then R3 and so on? Well, they permute the corners and they permute the faces. So if you write the permutations in cycle notation, here's, for example, what R3 does. It sends corner 1 to corner 2, corner 2 to corner 7, and corner 7 to corner 1. When you have 2 cycles, you can figure out what is the effect of doing one after the other. So I go through that here. Now here we're sending 0 to 3, and then the next cycle sends 3 back to 0. So it happens to not do anything on the 0. And it takes the 3 to the 5, and then the 5 is left alone here. And so if you follow this through with the 4 numbers that you can find in here, then you can find what's the product of these 2. What is the effect of doing one and then the other? Now sometimes you have 2 cycles where the product is not just one cycle, but where the product breaks up into 2 different cycles. And it's a general fact that I hope that they taught you in Math 42, that if you have any permutation at all, then you can write it as a product of disjoint cycles.
So does a approximation mean you first do the permutation on the left and then do the one on the right?
That is the more convenient way of doing it.
Okay, and then do you do the right permutation on the result?
Yes.
Okay.
Yes, so you have to, that's why I say, in this case, for example, you look at where does the 0 get sent by the first cycle. It gets sent to a 3. And then where does the 3 get sent by the second cycle? It gets sent back to a 0.
So in the right permutation, is 0 referring to the resulting element that's in position 0, or where 0 went to?
Well, this is the rotation, this is 063, that is R2. It is whatever R2 does. When R2 is this one here, and if previously something got in there, then R2 will permute those. That's how permutations work. So you're going to have to figure this out, and it's not really hard to write a Prolog predicate that computes where a given cycle sends a given element, because you just need to look at either it's a neighbor, and there actually is a predicate for neighbors in the standard library, or it sends the last one to the first. So you program those 2 cases, and then if you want to apply multiple cycles, then you kind of have to figure out what are all the possible elements. And you find that by flattening out and sorting. And so then you go through each of them and ask, where does it get sent? By doing this one cycle at a time. There's a bit of a recursion or a map or whatever, fold, whichever way you want to do it. So I'm giving you a couple of tips, but there are many ways of doing it. Do it by hand so that you know what you're doing, and then implement that in any old way. Once you have that, then really all that remains is to pick some number of rotations and then apply them all. And so I've given you a thing that picks all of the possible sets of size n with repetition and out of a given list, and because I couldn't find it in the standard library for some reason, and then now we have the 8 permutations. We have a target that we want to reach. For you, that target is going to be that you don't want to have anything happening on the edges, on the corners, so the corner permutation is the empty list. Then you want to know which pick is the one that makes it work, and n is the number of rotations to put together. So if you want to see, can I reach this particular target with 5 rotations or with 6 rotations, then you put in a 5 or a 6. And I mean, I put in all of them. And so this gives you all of the possible picks with repetition. Then this loops through them, and then you ask, if I take this rotation, does it reach the target? That's with the procedure that you wrote before. And that's all you need to do to find the ones that have this specific property that they leave the corners unchanged, and then you need to do it again to find a particular one. I'm only making you find 3 because these 3 suffice to do all the others, but when I run it myself, I actually read off the cube what permutation I want, and I ask it directly, how do I do that? So, that's that, and so hopefully that's not too difficult, but it took me a couple of days to do it, so and you need a little bit more high-powered Prolog than to do it efficiently anyway than what we had so far. So today's lecture gets you to be more effective with Prolog, so that you can do more than append. So the first idiom that you want to get is how to do procedural thinking in Prolog. So the way we've introduced Prolog is that you have these clauses. So this means H is true provided that B1 and B2 and so on are true. And that's declarative thinking at its purest, right? But you can use it to do procedural thinking. You can read this in a different way. You can say, I want to compute H, and I'm going to do that by first computing B1, and then B2, and then B3, and so on. And that's perfectly accurate, because that's really what Prolog does, right? It tries to prove the statements on the right-hand side in sequence. So, as an example, remember when we wanted to solve the factorials, where we wanted to find a number n so that its factorial is m. Well, that's what we want to be able to do, right? Now, how do we get there? So now, before that, you put the number of steps that you need. So we're going to generate a number between 1 and n, or 1 and m here. You're going to pick each of them in turn, and then you're going to try out whether the factorial relationship holds. So you can think of it as a step-by-step thing. Generate the numbers, pick one, plug it in, and then that procedural thinking is pretty easy. So if you're in a case where that works, absolutely go for it. It's an accurate reflection of how Prolog works. And it always works really well if the solution to the first step is the input to the next step, and the solution of the next step is the input to the third step. So whenever you can articulate a procedure that says, do this, then do that with the result, then do that with the result, and then check whether it's right, then Prolog is perfect for that. Yes?
Kind of like Euler's method of solving a differential equation.
Yes, except Euler's method has a lot more direction, right? It doesn't try everything.
No.
So here, this thing will just really try absolutely every possibility. So if you think about the tile puzzle with the flipping of the tiles, it will try every possible pattern in the first row by simply saying, let me first generate all those patterns, which, by the way, you did in the last homework. Then you plug it in, then you ask, does it work? So in the previous slide, we picked with member to loop through a set. When you recursively need to break something down, there's a variation of member that's more powerful called select. That's really very, very useful anytime that you have to do something recursive. So select XAR is true if X is an element of A and R is the rest. In fact, you've implemented that thing in the last homework. We called it without. And so you can think of it procedurally by saying, go through all of the elements X of A and then subtract them from X yielding R. But no, that's a very useful way of thinking about it. So I don't care about the implementation of select, so let me skip that. But it is really, really useful when you want to recursively pick an element, do something with it, and then deal with the rest. So here's the poster child application. I want to find all of the permutations of a list A. So I want B to be a permutation of A. What does that mean? So I'm going to use select and say pick an element X from A and store the rest in R. Then permute the rest into a permutation S, and then stick X in the front. That gives me all the permutations. Because over here there's an implied loop that says do this for all of the X's. Over here is an implied loop that says give me all the permutations. And then I just put them back together. So that's something that you want to look at as a model when you need to do something similar in the homework, where you need to do something with for all. So for all can always be done by using select or member. That way you can iterate over a set. And you want to use select if you need the rest. So in this case here, you can actually make a small simplification that you may or may not actually want to do. So notice over here, I say B is X followed by S. And you can actually plug it right back in. You don't even have to have B. So if you wanted to make your things look more concise and more elegant, you can, anytime you have an equal thing like this, the equal is complete fluff. You can always eliminate it. Because equal just means this thing unifies with that, and if you just plug it in, that's what Prolog does. Remember, all that Prolog ever does is unify terms. All right. Another useful tip, if you need to debug something, you can, of course, use the tracer, but not everyone is a fan of the tracer. Alternatively, you can put in print statements. So the way you do that is by using write on X, prints X, and then it keeps on going. So over here, for example, I have an example of where I'm generating the permutations in a inefficient way, where I'm saying to permute A from A to B, I say, well, I'm selecting X from A, and then I get a rest R, and then I stick X and R together in a different way to get B. And that'll work, but it gives me some of them more than once. And if I want to find out why, then I can put in a write-on in here, and then I get all of the R's printed out that occur at this point. So that's a simple and effective way of getting some insight as to what kind of looping Prolog is doing, what kind of things is it trying at a particular point. So keep that in mind. Now, as I'm sure you've all seen in the last homework, it is pretty easy to get a Stack Overflow by making an infinite search. So as an example, the first time that I tried to implement that lab in the game of NIM, where it says in the lab specification, it is so very easy to check whether T is at least 1 less than F. And so when I first did it, I said, well, so I want to move from F marbles to T marbles if T marbles has at least one less, or on the other hand, if I can go from T to something that's one more, and then I append even more than that, and then I can get it. And it didn't work. I got the right solution. So this is only the first half of the predicate, not the one with at most half. So I got 0, 1, 2, 3, 4, which are one less, and then I got a stack overflow. And so the reason for that is that I've asked it to do an infinite search. So you want to be able to look out for that. So it's, what do I know? I know the from, and I want to know the t. I don't yet know the t. But at this point I'm saying, give me all the t's, which I don't know, and concatenate it with nothing, with one marble, and all the s's. I don't know the s's either. So in here, there's infinitely many possibilities. So you never want to get yourself into that. You always want to be in a position where the next step works on a constrained set of possibilities. And in this case, it's easy enough to do. All you do is you flip these two, because the second append here, f is given. So the f is given here, and so then there's only a finite number of possibilities of decomposing f into s and underscore. That way, it's finite, so you put it first, then the second append works on a finite set, and all will be one. So at any time you get a stack overflow, ask yourself, where did you permit an infinite set of possibilities to be examined? And if you're not entirely sure, then you ask the other question. You say, is this thing finite? Is this thing finite? And it's easy to see if something is finite. You know for sure that append is finite if the last thing is given, if you already know it. There's a finite number of possibilities to do the appending. The same thing with member. Member is finite if you're exploring a finite set or select. So that's a useful thing to do. The other thing that's really important is to pick a good data representation. So I have one nifty assignment where you play a game with a set of 10 dice. And then you have to do something with the dice. I think you have to flip them, actually. And how do you represent them? So those 10 dice are there, and they get flipped, and then something happens, and then the next person has a turn, whatever. You could just have a list of 10 numbers between 1 and 6. Maybe it's useful to sort them. There is a whole bunch of queries that give you sorted results. And it depends on the game. Maybe it's useful, maybe it's not useful. You could use a map. You could use a list of pairs where the first one is the die and the second one is the count. Do you really need the 1, 2, 3, 4, 5, and 6 in the beginning? You could drop them and just make a frequency table where this is the number of 1s, the number of 2s, the number of 3s, and so on. And any of those, it might be a good representation. It really depends on what it is that you're doing. And so that is really kind of key. So if we look at this puzzle here, so the representation that I chose was to say a list of column positions for the first row, a list of column positions for the second row, and so on. And that turned out to be a really inspired choice, as I realized when I had to figure out how to get the clicks, because I have what the second row looks like. So I have, it's read in positions 1 and 2. Where do I need to make the clicks? In 3, 4, and 5. In the complement of what I have. Well, it's trivial to do a complement, right? Because all you ask is, make a union out of the two to get all numbers. And in fact, there must be a predicate for complement in the standard library. So that made it pretty easy. I've given you a link to an unhappy stack overflow query where they did something different. Their representation was to choose a list of, in this case, 25 integers. There would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then to compute the neighbors, they say, oh, that's easy, -1, +1, -5, and +5. And that is true, but the whole thing looks like a complete and utter mess in the end. So having a good data representation really is half the battle. So similarly with the permutations, I struggled with that. When I first looked at, that it is kind of complicated to put these cycles together, I said maybe I have the wrong data representation. Maybe what I should be doing is represent them so that I have pairs from, comma, to. And actually then the composition was pretty easy, but it got messy elsewhere. And then I went back to the cycles. I figured if mathematicians have done it for 200 years, maybe it's not so bad. So that is a key thing to be successful in Prolog. Another thing that is really useful, and I've used that several places in the homework, is to use higher order predicates. So just like in a functional programming language, you can use functions that consume functions. Prolog has predicates that consume predicates. You've seen one if you've looked at the grading script for homework 9, where I've used find all. Or I might have used setup. Find all and setup are similar. So they find all solutions for a query. So here I say, this is directly from the homework grading script, find me all x such that something is true, in this case that x is a subsequence of A, B, C, D, E, F, and collect all answers in a set S. So that if you ever need the solution of a predicate, or really of any query, if you need the solution of any query in a set, find all, we'll just put it in it. Now, you often don't need it, because if you want to just do something with them and go on, then you could just use subseq without the find all followed by member or select, and that way you also do through. But sometimes you do need it. Find all has a couple of variants. If you want to collect multiple answers, you then collect lists like that, lists of variables, and then your query has to have more the x and y in there as well. And then you get a list of pairs, a list of lists of linked trees. If your query is composed of more than one statement, then you need to put them in parentheses. So here I want to find all x, such as x is a member of L, and x is not a winning position. Now, in Scala, we have things like filter, that we can include only things that match a certain predicate, or there's a filter not for excluding the ones that match the predicate. So I needed to use that in one spot in homework 10, where when you compute this product of cycles, you get a list of other cycles, and you want to throw away the ones that have length 1. Because a cycle of length 1 does nothing. Like here, the cycle 5 maps 5 to itself, so I might as well not have it. And how do you throw those away? The simplest way is to use exclude. Exclude takes a list and a predicate, and then it throws away all the ones that fulfill the predicate. So you can make yourself a little predicate singleton, where if you say something is a singleton if it has length 1. Okay. And this way you exclude then all of the singletons. Now, you don't even have to make a predicate. You can use a lambda. Here's how you write a lambda in Prolog. You say exclude takes the thing in red as the predicate, and so it is the lambda is written with a greater. So we have the function that takes an x, and that is true if x can be unified with a list of length 1. Yeah.
Why do you change the order of the inputs when you use lambda?
Oh, maybe I'm wrong. One of the two must be wrong.
Okay.
Yeah. I'll need to fix this line. So there's an include that works exactly the opposite. It keeps the ones that match the predicate. So include is the exact same thing as filter. So if you feel that you want to filter, then include is your friend. If you want to filter not, then exclude. Well, if you have filter, of course you want to have map as well, and you do. So if you're ever in a situation where you have a list of things, and now you want to apply a function to them, then you kind of can. There are no functions, of course, in Prolog, but there are predicates. So I'll give you an example that I used in the homework. I get I might get a list of permutations like this, and then when I look at it, I say, well, I don't know how to twist a cube like that. I want to know the labels of these permutations. So I made myself a binary predicate name, where the input is the permutation and the output is the name, or the other way around, whichever way you want to look at it, it's a predicate. And then I use map. So by mapping the name function, then it's applied to the first element and then the second element, and I get this list of rotation names. And so anytime that you have a function that you want to apply to all of the elements of the list, use map. Map has always been a good thing, and you have it in program. Yes, and you even have fold if you want it. So if you wanted to write an arbitrary loop, you can use fold in the way that you know and love, where you need to provide a function that is applied at each stage. So here I'm having an example where I'm adding up all of the elements in the list. You don't need to do that. There's a function called SUMList that does that, but let's say that wasn't. Then I can use fold. I make an add predicate so that that sum is the sum of x and y. And then I have a list. I have an initial element for the fold, and out comes the sum, which in this case would then compute 0 plus 1 plus 2 plus 3. If I don't want to make a predicate, I can also make a lambda that you see here. In this case, that would be a ternary predicate because I need to have the input from the list, the input, I guess the x is the left fold. Okay, so the x is the list element, the y is the intermediate value, and then you just compute the answer here by hand. So either way, you have all of the higher order functions that you use from functional programming available for you in program.
Sure.
Yeah.
Can you do more
Yeah. So find all has three parameters: a variable or list of variables, a query where that variable occurs, and a thing that holds the answer. And it does exactly what it says. It finds all answers. So the last recommendation is know the standard library. The documentation is not exactly pretty. It's definitely being caught in a time warp. So that's what the web looked like around 1985. And yeah, I mean, let's open it up. But we can find a way around. So there's a whole bunch of useful list operations. Any list operation that you can imagine does probably exist. Like I've used flatten in the homework. Flatten does, what do you think it does? It has a list of lists and flattens it into just a single list. There's a way of sorting something. So there's a notion of ordered sets. You can have set union, set intersection. I should have put sort on here because sort is useful. If you needed to deal with frequency tables, there is a function that the set of functions for maps, maps in the sense of key value pairs. We've talked about the accumulators and higher order predicates. When you look at the standard library and look at a particular function, let me show one. Then you'll notice that there are these various, it says here's a question mark element, question mark list. Here it has a plus list of lists, question mark list. And what these things mean is a question mark means that thing could be an input or an output. A plus means this can only be an input, and a minus means it can only be an output. And so that's obviously something that's useful to know. Sometimes you see a :G, and that's used for higher order predicates. So that is, it stands for goal. So that means it's some predicate. So when you look at the documentation for include or exclude or a map, you'll find this. So that's really all you kind of need to know to be dangerous in Prolog. And so I tried this out with a simple lab. So I found this game here when Googling about, called the 31 game. The way you play it is that you have 24 cards by just grabbing the cards, ace, 2, 3, 4, 5, and 6 from a standard card game. And each player turns over a card of their choice. And so this would player A might turn over the 3, player B might turn over the 8. The first player who makes the value of the turned over cards go to over 31 loses. So you do not want to be the first one to go from 31 or below to 32 or above. So that's the game. Now, of course, what we want to do is we want to make it so that the computer can play it perfectly. And for that, we need to do things like figure out how to move from one game state to the next. So it would be a good question. What would be a good representation of the game state? Like we've done representations of the NIM game with pebbles and numbers. And here, think of 3 different representations of this game state. Then here I'm asking you to compute, how do you compute the value of a game state? Here I'm giving you a particular representation, and I want you to compute the value, because if you did this in Java, you would write a for loop with an integer index, and let's say you had something like that. How could you simulate that in Prolog? And so it's not hard to do that. You would say, well, you'd have to use recursion, and so you'd have to use this index as a helper parameter somewhere, and it gets you here, guides you here on how to do that. And then it says, how do you compute possible flips? And it guides you in a way to do that. And then finally, we want to actually play the game and win that. So go through that, and in fact, it's a good idea for you to spend a few minutes playing the game. I've brought enough card games for all of you to do that. So that way you get some basic idea what it's about. But don't fritter too much time away with that. Do the coding, and then we'll talk about it. Okay.
Any magic tricks?
And the last 10 minutes going through this together.
The sum of whatever.
So I asked for 3 different representations of the game state. We have one on the next slide where we have a frequency list where this is the number of aces, there's no 2s, there's 2 3s, and so on. So what other representations could one have chosen?
A Boolean array?
Or a Boolean array of 24 Booleans.
Yeah.
Okay. Yes.
So you could have 2 lists of all the individual cards. One's for chosen and one's for not chosen.
Okay, so a list of cards for the chosen and then the complement of that.
Yes.
What else?
Oh, the different representations.
Yeah.
So you have frequency table of available, frequency table of taken,
Okay.
individual cards are available and individual cards taken.
Yeah. Or you could have, just to give another one, you could have a map where you map each card name to the number of cards that are already taken. For example, right? So there's any number of different representations. So I pondered those, and I said, well, the frequency table of the ones that are already turned over, that's the one that I'm going to go. So now we need to compute the value of one of these states. So this thing here, for example, would have value, well, this is a 1, so there's no 2s, and there's 2 3s, so the value of this thing would be 7. So in general, to go to the value, you would, if you had to do this in Java, you would have a loop, right? You would have an index I that you multiply with each of the values in this list, and then you would add them all up. Now, how can you do that in Prolog? Actually, one person in the previous section said, you don't really need a loop. You could just say 1 times the first element plus 2 times the second plus 3 times the third and so on. But that's certainly true, but I wanted to practice, what if you do want to have a loop. So you don't specifically have loops, but there are ways you can make them. So here's one possible way of doing it. Very pedestrian, not maybe super elegant, but it definitely works. So we say that we are going to make a recursive function, and we're going to have a helper variable that I call s here. Maybe I should have called it I, that gives the current position. And so then I'm starting out here and say, okay, so we're multiplying x, that's the head of the list, with s, that's the position number. And then I want to recursively call value on the tail with s plus 1. And then I get an answer back. And then I want to add that answer together with what I get from the head, right? So here is that. So I call value of the tail s plus 1, and I get an answer that I call n1. Except I can't call s plus 1. Why can't I put an s plus 1 in here?
Because it does not evaluate it?
Yeah, it wouldn't be evaluated. It would then try to match, and then you would get like 0 plus 1 plus 1 plus 1 plus 1, and would be no good. So we force evaluation by putting s plus 1 to the right-hand side of an is. That stuffs it into s1. And then we get an answer n1. And then the n that we want to have is then, of course, p plus n1. So, and you can read it from left to right, right? I first compute this product. Then, okay, I have to do the silly increment. Then I have my recursive call. And then I assemble the final answer.
What was that again?
N is the answer. Because it's a predicate, right? So you always need to have a slot for the answer. So that's really all that one needs to do here. Now we want to compute possible moves that we can make. So I have a list such as this one here. I want to know what are all the next moves that I can make. So, and we're not yet worried about whether it's a winning or a losing state. I just want to know what flips can I make. Now, I can change a 1 into what? It can only go up, right? And if you have like a small number of possibilities, it's often easier to just list them all, like I've done here, and say these are all of the possible flips, than using arithmetic conditions. You could do this with a condition, and you could say you can move from n to n1, where n1 is n plus 1 and n1 is less than 5. You could do that, but it is so much simpler to just list all of the possibilities. That way you never have any issue with Prolog not being able to do arithmetic or guesswork, because Prolog can surely try these all out. So whenever there's a small number of choices, do that. We're doing that in the homework with the rotations. I just have a predicate for what these rotations are. There's 8 of them. I give them names. I have the corresponding vertex and face rotations. And so that's a really easy way of doing that. So now we want to be able to say, how can I go from a from list to a to list? And so of course what I want to do is I want to grab one of these here and just flip it. To flip it means, if it's is to do what it says here. So in this case I would turn it into 1. That's the only possibility. So how can I go through a list and say I want to flip each of them? We kind of know how to go through a list. You can use member or select, but it doesn't put it back in the right place. So there is an append trick that works for that, and here it is. So I say I'm going to find x sitting inside my list f. So here's my list f, and I'm finding x by saying append a with a list that starts with x and has other stuff, so that you get to the list f. That means the x is sitting there somewhere. So then I'm going to flip it to whatever it is. That increases 1. And then I'm going to put it into the same space. So that way I have edited in place. Now that's actually a very nifty way of doing it, right? And I've now done that for all of the possibilities. So for all of the possible positions of x, I have now applied the flip thing to it and added 1 to it. So that's a nifty trick to know. Anytime that you need to edit something in place, then use this append. Now the rest of it is now completely smooth sailing. So I wanted now define what are all the moves. Well, a move needs to be one of these moves, and then the value needs to be less than 32. So now I have a move predicate, then I can have a win predicate, like we've had in the games that we've played before. And now if you ask, when nothing is flipped over yet, this is the game position I have right now, so the computer starts, nothing is flipped over yet, and so when you ask this, it's going to take a while, and what's it going to say? What do you think it's going to say?
It's going to take a very long time to try to solve all.
Yeah, and then what's it going to say?
Exactly. No.
And it actually didn't for me. It said true.
Oh.
So you were in 50
So that's it is a winning position, right? But that's nice, but it doesn't really tell us what to do. So the way to do that is actually very easy. Whenever you want Prolog to reveal something, you just introduce another variable. And so I call that variable y. That's the next move that one needs to make. And what is it? So it's move x to y. And that's the next move where it's not a winning. So it's exactly the same, except that I'm now revealing the y by sticking it into the predicate. I also got tired of doing the arithmetic by hand, so I'm adding a third thing in here, and that is the value. So let's try that. So we're going to start playing with nothing. It takes a long time. Now the computer wants to flip the ace. Okay, what do we want to do?
Flip the 6.
Okay, you want to flip the 6. So at this point we have the ace flipped and the 6 flipped. And we'll see what the computer wants to do. The computer wants to flip the ace. Okay, what do we want to do? Yeah. Okay. You don't even want to try. Okay, I'm going to flip the 6. Okay, now the computer comes back really quickly and wants to flip the ace again. It's going to run out of aces pretty soon. In the interest of time, I will flip the 6 again. So, and it wants to flip the ace again.
It's reminds me of war games. The movie with the computer that plays tic-tac-toe, like Wages War.
Alright, so now the computer wants to flip the... So I have flip the 6.
Oh, yeah, we lose pretty much.
So the computer flipped the 6. Okay, and so now I lose? Yes, because I don't have an ace to flip anymore, so I have to flip a 2 and I get to be over 32.
Yeah.
Alright, so the computer wins. And with what? 8 lines of prologue? 9 lines of prologue? Okay.
It's possible to force it into a losing position if you give it a losing position?
Yes, if you start out with a losing... so if I start, then I'm going to... I can force a win by simply flipping the ace. Because that's what the computer did. So with this particular game, you always want to start.
But it doesn't tell you what the next move would be after.
Well, the program, because it doesn't want to print out the whole game tree, so you have to do it a step at a time. Yeah, it would be too tedious otherwise to interpret the output. All right, so as you can see, Prolog can do way more than just append. And so I hope you enjoy the homework.